Hello, everyone, and welcome to our August 2nd live session. Thank you for joining us. My name is Matthew. I'm one of the staff members at Steward Observatory, and I help Professor Impey with our online classes. Thanks for joining us today. We are excited to have you here. We are going to talk about all sorts of fantastic astronomical questions. As usual, if you've been here before, you know that you can post questions in the chat. We will grab those from there. If you haven't been here before, welcome. We grab questions from the chat. We try to pick a variety of questions. I generally try to go in order, but we do skip around from time to time to pick topics that we haven't covered before, or to give other people a chance to ask questions. I also wanted to mention that for those of you who are on our mailing list, I sent an email with a mistake twice, and I meant to correct it this morning. In 3 weeks, we have a live session on August 22nd, but that's a Monday, not a Tuesday like it says in the email. The next time I send out a reminder, which it will be before our next live session, I will correct in that email. So, Chris, if you want to welcome everybody, then we will get started with their questions.
Okay, welcome everyone to the live session for the online classes and anyone else who finds us here. And I'm glad to take your questions on any topic in astronomy.
The first question is from Supreme Scientist, who's on with us live. Have the constellations changed since Babylonian times in terms of stars dying or being born?
That's an interesting question. Not dramatically, because the lifetimes of stars are, of course, huge compared to the lifetime of a human civilization. So civilizations, the Babylonians, maybe 6,000 years ago, and a typical stellar evolution timescale is millions of years, even for the most massive stars. Now, by chance, it is possible that a star could die, go supernova, and then leave behind a stellar remnant. And undoubtedly, a few constellations have been affected by the disappearance of a star as it died as a supernova. But supernovae are rare events, and there are only about 6,000 stars visible to the naked eye. So the odds that any of them would disappear are actually quite low. Also, while stars do move in three-dimensional space, their space motions are modest compared to the distances to those stars. And so while stars do shift in the constellations, their relative positions, it's pretty subtle. So between Babylonian times and present day, you would have to have a photographic memory of the sky to notice any particular difference. What does change, of course, is the precession of the Earth spinning on its axis with a 26,000 year period. And that is pivoting the sky in terms of the constellations that are visible. So Polaris is the pole star now, but will not be in the future and was not in the distant past. In Babylonian times, Egyptian times, a star that they called Thuban was the pole star. So while the constellations themselves don't change shape or move around or have stars come and go, their relative positions in the sky to the celestial equator and the celestial pole have shifted due to the precession of the Earth's spin axis.
Excellent. The next question is from Mars, who is on with us live. If we look at the sun, we see approximately 8 minutes in the past, and so with other stars, billions of years in the past. Why is it that we always see the past and we can't see the future?
Well, yes, it would be nice to see the future, or maybe not sometimes. So it's the finite light speed travel. So light has a very fast speed, 300,000 kilometers per second, 186,000 miles per hour if you insist on non-metric units. And that's essentially instantaneous on the Earth, but of course it adds up to significant time when we're out there in the universe. If light traveled with infinite speed, we'd see the entire universe as it is now, and there'd be no time delay, and everything will be simultaneous and contemporaneous. But because light has a finite speed, we essentially have to wait for the messenger, photons, to reach us. And that's why we are always seeing it in the past, because there's a time delay, and that means a present event in a distant part of the universe takes some period of time to reach us. There's no way in the causality that's underlying physics for us to be able to see in the opposite direction into the future to events that haven't yet happened.
Excellent. Thank you very much. The next question we have from a live viewer is from Dion Mack. I read an article that the Earth experienced the shortest day ever recorded last month. Do you know why this was so?
I think I was aware of that article. I mean, these are tiny effects. Timekeeping with atomic clocks and with very accurate celestial observations is exceptionally accurate. And so we can measure the day, we can measure the period of the Earth's orbit to tiny fractions of a second, millionths of a second. The Earth does have irregularities in its orbit, and I think it was just a fluctuation, a statistical effect that made that particular time slightly shorter than any other. But remember, this is by a tiny fraction of a second. These are not sort of fundamental big changes in the Earth's orbit.
The next question is from Manashi Paul, who has a bachelor's in biotechnology, but is interested in possibly a master's degree in astrobiotechnology. So Matthew, I'm not even sure what astrobiotechnology is. She would like to know how to pursue that. Have you heard of this field? Do you know, can you talk about what it is and how someone might pursue it?
It's a hybrid field, obviously a hybrid of three things. Astronomy, biology, and technology. Astrobiology is a well-established subject with a history going back 50, 60 years and a number of professionals working in the field. Biotechnology, the other polarity of a three-term combination, is of course a huge field, an industry that employs hundreds of thousands of people worldwide and is a huge economic driver these days. Astrobiotechnology is a very small niche, and one that I'm not really aware of as a real profession. I imagine it would be the use of technology in astrobiology, or the application of technology to deciphering life in the universe or understanding the role of life in the universe. In the sense that astrobiology uses technology anyway, telescopes and other instruments to look for life around the solar system, I think technology is always a part of astrobiology. So if you're talking about working in astrobiology with a technological focus, then that's entirely appropriate, because that's the way the field is headed, because we're doing more and more refined experiments either to detect exoplanets or to try and look for life around the solar system, or eventually life on other planets.
Excellent, thank you. The next question is related, and as somebody who's interested in pursuing a career in science or in space science, and would like to know, how does one apply to NASA, or how does one get a job at NASA?
Well, NASA is a huge federal agency. They have a budget of about $19 billion a year and hundreds of thousands of employees. Now, I think 80% of NASA employees are contractors, so they're not scientific civil service employees. That's a smaller fraction. That's only a few tens of thousands. So NASA is distributed at a series of centers around the United States, I think 10 or 11 NASA centers, the most famous of which are, of course, Johnson Space Center in Houston, Kennedy Space Center in Florida, and NASA headquarters in Washington, D.C., and JPL, perhaps, in Pasadena. And these have job openings. I mean, there's a continual churn in the staff and also in the contractors. One of the ways to get into NASA is to start by being a contractor on a project and either liking it or doing a good job, or both, and then finding one of the more hard to get, precious, if you like, civil service positions, which are fairly secure actually once you get them, and moderately well paid. So I would say, as a big agency, NASA probably has hundreds of job openings at any one time, and I think the way you start is to go to the NASA headquarters website, and they will have a job page. I haven't been to it for quite a long time, so I'm not exactly sure where in their web architecture it is, but you can certainly see NASA jobs that are available at any given time. Most are on the technical side, of course, mostly engineering.
Excellent. The next question is from DS, who's on with us live, and asks, is the scientific consensus that Jupiter and Saturn migrated into their current position, or is that merely speculation?
Well, it's speculation, but it's speculation that is approaching a firm consensus, and is based on the understanding and the awareness that planets do not stay in fixed positions over the history of the solar system. So we have pretty good evidence that if we simulate our solar system and how it formed, we can't actually make models that form Jupiter and Saturn where they currently sit. Also, if we form our solar system, there are events in the early solar system in particular where the orbits are a little chaotic or unstable and the planets rearrange themselves. And not just Jupiter and Saturn, but Uranus and Neptune as well, not so much the inner planets. So the consensus has emerged, indeed, that Jupiter and Saturn did not form in their current locations, but they swapped positions, and there was a rearrangement of the outer planets too. This happened fairly early in the first billion years of the solar system.
The next question is from Sophia. How can the universe be finite when it was born out of a Big Bang singularity?
Well, the singularity of the Big Bang is, of course, difficult to understand. In fact, it's essentially a nonsensical idea in physics because a singularity implies infinite temperature, infinite energy density, and infinite mass density, and those are not physically reasonable. So we don't actually understand the singularity. The universe being finite from an emergence in the Big Bang event with space-time unfolding over nearly 14 billion years is simply a statement that we have a limit to our vision. So the universe has a boundary or horizon, but it's not a physical boundary. It's just a boundary to what we can see, because we can only see regions from which light could have reached us in 14 billion years. So that's the sense in which the universe is finite. There's nothing at all about the Big Bang model or about cosmology or measurements we can make that suggests that space-time itself does not go beyond the visible limit, the finite limit due to light travel time, and extend far beyond that.
Hey, sorry, I'm having a little delay in my internet today. I apologize. The 800 millimeter telescope project is on with us live and asks, science and philosophy had a tight relationship from pre-Socratic philosophers onward. Maybe it started waning in the last century. Is there any modern philosopher or reading that you can recommend?
So philosophy has a strong connection to science, of course, because science depends on the fundamental way we ask questions about nature or how we decide something is true or not true. And you know, philosophers' methods are important in that regard. Physics has been known as natural philosophy. In fact, at the University of Cambridge in England, a physics degree was called a natural philosophy degree until I think the 1960s or 70s. So the separation between science and philosophy is not as strong as some people think. But they're very different disciplines. Academic philosophers get trained in a rather different way from a scientist, so it's actually difficult to do both. There are some philosophers who are, deciding to do science and study science. They don't actively search for new knowledge, but they scrutinize how scientists make their decisions. And so there is a field of academic philosophy that looks at science, the scientific method, how science works, the history of science, what status science has in the intellectual world and also in the societal world. And so these are not a large number of scholars, I'd say dozens rather than hundreds, but there is some philosophy that's part of science at the moment.
The next question is from David Gold. With regard to the first images from the James Webb Space Telescope, what causes the stars to appear to be eight-pointed?
That's a feature of the geometry of the James Webb Space Telescope. So if you have a simple, sort of fundamentally simple symmetric optical arrangement, you will generate a two dimensions of diffraction spike. So it'll be a straight up and down and a straight sideways diffraction spike. If you remember, the James Webb Space Telescope has hexagonal mirrors, and they're put together into the configuration that makes the telescope. And so that adds a second and a third axis, actually. And so you get a more complex diffraction spike that consists of 8 points instead of 4.
Tony asks, Einstein's explanation against the uncertainty principle logically seems to be right. What are your thoughts on his arguments against Heisenberg?
I missed, you cut out for a few words of that question.
I apologize. Einstein's explanation against the Heisenberg uncertainty principle logically seems to be right. But what are your thoughts about it?
Einstein's fundamental objection to Heisenberg's uncertainty principle and sort of some of the foundational ideas in quantum theory were the fact that he did not accept that there was a floor to our knowledge or our understanding, because that's what the uncertainty principle says. It's really an imprecision principle, not an uncertainty principle. And it says that there's a limit to our ability to measure certain quantities, especially in conjunction, like position and momentum, or energy and time, and that's an unavoidable limitation. It's got nothing to do with the measurement apparatus or the experimenter. It's built into nature. And Einstein was unhappy with that because he thought physical theory should be able to derive truth. They should be able to derive certainty at some level. And so he cast around for many years, decades actually, for ways to circumvent this limitation of quantum theory. But as far as we can tell, he was wrong. There's no flaw in quantum theory, and there's no successful theory that's shown that the imprecision of Heisenberg's principle is an illusion. And really, if we look at it a different way or with different tools, we could circumvent that limitation. That limitation holds in the lab, it holds in all the physical measurements we make.
The next is from Mysterious Gamer. We get this question not infrequently, but we haven't addressed it in a while. So can you talk about, so this person is currently studying A-levels and wants to pursue astrophysics at the university. Can you talk about what subjects in physics are important to learn and how much significance other sciences like biology might have?
Right. So if you're heading for astrophysics and you know that, and you're studying a physics degree, either in the US or since you're taking A-levels probably in the UK, you can tailor the classes you take in physics as an undergraduate to smooth your path towards astrophysics. Now, generally, there's not too much choice because most physics degrees, including ours here in Arizona, have a standard sequence. You're always going to be taking foundational courses, such as in the first year, such as quantum, electromagnetism, optics, thermodynamics, and so on. And those are actually important topics to know as an astrophysicist. So the foundational physics courses are definitely relevant, and they're required anyway, along with the math. The choices or options or electives happen later on in the junior and senior year, typically at a university. And so that's where you might want to pick. And therefore, if you have a choice and the department has sufficient offerings, obviously take an astrophysics class. If you could, take a plasma physics class, because a lot of the universe consists of plasma, that fourth state of matter that involves very hot gases where the electrons have been stripped off. Taking an advanced optics course is a good idea because you may want to get into the instrumentation of astronomy, optical astronomy, infrared astronomy, and then having a sophisticated optics class will tell you how mirrors are built, how spectrographs are made, how many astronomical instruments are made. So these are classes you might want to pick up on. And if you're interested in high energy astrophysics, then taking a high energy physics course would make sense.
Thank you very much. I appreciate that. Kevin Sharma asks, do you think that computer science will be the future of humanity, or will it be astronomy, specifically astrobiology and observing exoplanets and exomoons?
I'm not sure we could be so grandiose as to claim these as the future of humanity, but in terms of subjects that will retain their relevance and attract more people and be strong subjects to study in 10, 15, 20 years, astrobiology is a very safe bet because really we're only in the early phases of finding exoplanets where we essentially are just detecting them in large numbers and almost know nothing about them except mass and size. The future generation of instruments will start to characterize exoplanets and eventually find life on them or not. And so astrobiology is a very strong bet for the future. Computer science is always going to be a good bet for the future, independent of astronomy and the applications. Astronomy depends heavily on computers and supercomputers and simulations, and that's not going to change. And essentially all fields of science are now using big data, and therefore computer science is almost a foundational skill for many scientists, and an increasing number, I think, in the future.
The next question is from one of our live participants. What have we learned so far from the James Webb Space Telescope that we didn't know before the first images appeared?
That's a good question. So I think the early science data has been spectacular because it's shown just how well the telescope is performing. But the truth is, scientifically, we haven't learned a lot yet. Remember, what we've seen so far in the first press releases was just hours worth of data, or maybe a few days worth of data. And this is a telescope that's going to be working for 20 years, we hope. So it's holding the bar a little unfairly high to expect a lot of science to come out of that first data release. That was really just an affirmation that the telescope is working as advertised, and it is. So the simple answer is we haven't learned a lot. Those images were spectacular, but I would say for people who work in the fields of nebulae or colliding galaxies or gravitational lensing or any of the things you saw in those images, there's nothing fundamentally new in what we saw.
The next question is also from a live participant. Lyrics Nep asks, in our solar system, other than Earth, that could potentially support life?
There's a critical dropout. Is there any place that could support life? You have to repeat the question because you dropped two words that were critical.
What's the best candidate in our solar system, other than Earth, that can potentially support life?
Well, it gets the lion's share of the attention in some views of planetary scientists who like the outer solar system too much, but Mars is still the best candidate for life beyond Earth. But that's not on the surface. The surface is arid and extremely cold. It's a frigid, arid desert, temperature below the freezing point of water. So there's no liquid water on the surface of Mars, or very little hints of it. However, underground, Mars almost certainly has liquid water aquifers kept liquid by heating from the interior and pressure from rock and ice on top. And it may have some underground seas or lakes that are quite substantial, and especially in the polar regions. So Mars has all the capacity for hosting microbial life underground, maybe quite far underground, tens of meters or hundreds of meters, not anywhere we can reach with our instruments. So it remains the best place to look for life. Second best beyond that is hard to tell. Europa is a favorite candidate because, of course, it's an ocean world. It's completely covered with an ocean under an ice crust. And there's sufficient heating from its interior that even though it's far from the sun, life could exist in that tepid or cold environment as it does in cold environments on the Earth, near the Antarctic, for example. So those are the two best candidates. And if you wanted to be out of the box, the third one would be Titan, which is a large moon, has an atmosphere as thick as the Earth's and made of almost the same stuff, nitrogen mostly, and it has lakes of ethane, methane, mixed with a little ammonia and perhaps a little water. That's not a conventional chemical environment for biology, so biology, if it exists on Titan, would be a completely new variation on biology, but that's what makes it interesting.
The next question is from Arya. Earth is home to us, but we know there are people who are trying to build a civilization on Mars. Do you think that there's any way that this could harm human health?
Well, living on Mars will be hazardous. Getting to Mars will be more hazardous, actually, because the spacecraft, to be not too heavy, are not going to have a lot of shielding. So you'll be exposed to cosmic rays, high energy radiation for an 8 to 9 month trip. And you'll get more than a lifetime's dose of radiation in that 8 or 9 months. And the trip itself is hazardous. Living on Mars could be less hazardous if the infrastructure has been built ahead of time, and probably it would be. The first Mars base will have been staged by many missions ahead of time, and some of which didn't have people, involving robots that would be doing some of the work and robotic factories that would be generating building materials and so on. And the idea is to create a habitat that's sufficiently insulated from the Martian harsh environment of radiation, of course, and very thin atmosphere, that the occupants would be fairly safe. So there's nothing intrinsically dangerous about living on Mars if you have the right protective environment. I think the biggest hazards to any inhabitants of Mars is psychological, because the degree of isolation is really extraordinary there.
The next question is from Mysterious Gamer, who asks, do we have any other methods to know the distance and masses of the stars apart from the wobble method and redshift?
Distance and masses of stars masses are hard to measure for stars. You actually need a stellar model because the mass isn't sort of printed on a star. When we observe stars, really we just see their temperature, and if we know the distance, the luminosity. So the key idea actually that's being played out by the Gaia satellite, which is from the European Space Agency, is to do essentially trigonometry, to use the parallax method. So parallax is a method that really typically only applied to very nearby stars, maybe 10 or 100 light years away, where essentially you use triangulation for measurements from the Earth at two different sides of its orbit, so that's the baseline, and then you look for small angular deviations to generate a long skinny triangle, which lets you measure the distance. And from the distance you can calculate true size, true mass, and so on. The Gaia satellite is extending this parallax method, which had only been applied to thousands of stars until fairly recently, to 1 billion stars in the galaxy. An extraordinary, maybe 1% of the galaxy is going to be measured to distances of several thousand light years. So that's an extraordinary advance using this basic parallax method, and we'll have physical information for those billion stars.
The next question is from Azam, who is on with us live. How can we be sure what counts as a biomarker? Is it possible that on some planet life completely different from us exists and they might breathe nitrogen instead of oxygen? How can we be sure that what we call biomarkers are actually signs of life?
This is a big issue in astrobiology, to understand what a biomarker means and what's sufficient evidence to declare that you've detected life. And yes, the problem really runs two ways. It runs in one direction. It means we can think that we have a biomarker that would indicate life, such as oxygen and ozone in the atmosphere of a planet, because in our planet it was put there by biology. But what is sufficient to declare that? Because oxygen can actually be created abiotically, that is, by geological processes. You can generate free oxygen. It's hard to generate as much oxygen as the Earth's atmosphere has, but some people pushing the model say you can get 10 or 15% oxygen in an atmosphere of an Earth-like planet. So you can have a biomarker that, to our current knowledge, seems like a very good one, where the water is muddied by the fact that it can be produced abiotically. But the bigger concern, as the question alludes to, is that we can only look for the things we know, or the things that are modeled on biology as we understand it, or our form of biology. If you're looking at a metabolism that has as its input and output different gases or different materials, then maybe we're not looking for the right thing. There was a time on Earth when the metabolic output of microbes was not oxygen but methane, and these were methanogens, and so methane would have been the key biomarker. There may be other planets where there are different biomarkers entirely, and we'd have to understand alternative and strange forms of biology to be able to predict those. Since we have no other examples of biology in the universe, we don't know how to do that. And so that's a big uncertainty over the whole search for biomarkers.
The next question is from who's on with us live. Why do we think that phosphine gas detected on Venus might be a possible sign of life?
Well, the phosphine detection on Venus has, essentially been deconstructed, if you like. So they're on two grounds. In principle, phosphine is a gas that on Earth is found in very small trace quantities, but is only associated with life processes, biological processes. On Venus, it was found in a very small amount, parts per billion, and the detection itself was controversial because people wondered whether that spectroscopic signature of phosphine might have been some other signature. When you don't know all the ingredients in an atmosphere like Venus is, it's really hard to tell what might be a contaminating signal, confusing with phosphine. So there was the actual question of the detection itself, because it was a weak detection, and then there was the interpretation. Is it really phosphine? And then the third level would be, did the phosphine, if it were there, indicate life. And I think on all grounds this story has sort of evaporated a little bit. The detection was not as strong as originally claimed. There was an ambiguity about how to identify the spectral feature and be sure that it's phosphine. And it's not even clear that phosphine at that very, very low level does absolutely an indicator of life.
Excellent. The next question is from, again, one of our live participants. Nita Frank asks, if a lot of our Earth's internal heat is by radioactive decay, then why isn't lava radioactive?
Well, actually, lava is very mildly radioactive because all rock has naturally occurring radioactive elements in it. So, but it's very mild. So lava is very, very mildly radioactive, just like any big rock is, or any rock. The heat from lava is obviously coming from a different source. So the heating, the interior heating of the Earth is coming from a very dense part of the Earth. So when the density is high, as it is, of course, in the core, the rocky, the solid, and the liquid core of the Earth, then the concentration of the radioactive heating is stronger. And so that's why the Earth is hotter in the core, and that heat flows out to lower density regions and gradually cooling as it moves outward. Lava, hot lava, and other molten elements of rock are produced by tectonic activity. So this is just essentially heat transfer traveling through the body of the Earth. And in fact, in the mantle of the Earth, the mantle, while it is essentially rigid rock, if you looked at it from day to day or week to week, over very long periods of time, it's actually moving around. There are huge sort of viscous convection cells of rocky mantle material. And it's, again, just heat moving out from the interior to the exterior. And in the sense that it's driven by radioactive decay, it's because the radioactive decay is concentrated in the center of the Earth.
The next question is from VM. Why don't all the planets collide with the sun, as shown in experiments with space-time mesh in which all the balls collide at the very end?
Well, the solar system is not stable over the very, very long term. So people have run models, simulations with supercomputers of what the stability of the solar system is. And on very long time scales, where I'm really talking tens or hundreds of billions of years, so long after the sun has died. The sun, of course, will die and leave behind a white dwarf in the end, which is about 2/3 the mass of the present-day sun. So that weaker gravity of the sun will not hold planets, so the most likely outcome on the very long time scale is that the planets actually evaporate or migrate off into interstellar space, not collide with the sun.
Gaidamaka asks, or Sophia Gaidamaka asks, do you have any tips for beginning astrophotographers? How can amateur astrophotographers bring discoveries and innovations to astrophysics?
Well, astrophotography is, possible with the cell phone cameras that most of us have in our pockets every day with iPhones or Samsungs or whatever our device is. They're very high quality cameras, and you can buy adapters quite easily, and they're not too expensive, that will fit an iPhone or any phone to the back of a small telescope and let you take timed exposures. And the cameras, of course, allow for timed exposures. So that's an easy entree into astrophotography, just using your phone and any small telescope with an adapter that you buy. For slightly more sophisticated astrophotography, you can use an SLR, sort of more traditional camera, which has, of course, a lot more light gathering power, especially when attached to a telescope, and quite a big CCD and a lot of sensitivity. There are entire books written on this, so I would recommend that, of course. And especially a magazine like Sky and Telescope and Astronomy, hobbyist magazines have a lot of information about this. They have articles almost every month about astrophotography, and they will also be able to recommend a lot of resources, including some that are free and online.
Next question is from Nashan Adero. Are thought experiments common nowadays in science? Who has been conducting thought experiments the way Einstein did with a major breakthrough many years ago?
So thought experiments have an important role in science. So it's an interesting question to ask what their status in science is now in the modern era. They were very famously useful in early physics, in the pioneering days of physics with Einstein and Bohr and Schrödinger and Heisenberg, because they allowed people to imagine experiments that might be actually quite difficult to do. I would say astronomers still use thought experiments because astronomers can't measure all the parts of the universe they're interested in, and they can't do physical experimentation on objects that they might like to, such as black holes. So astronomers use thought experiments quite a lot, especially regarding ways of teasing out the properties of black holes or objects we know to exist but which we can't do easy measurements of. So certainly astronomy and physics still use thought experiments. It's not as clear that other fields do. I'm not familiar with biologists doing thought experiments, but I've heard of some cases where biologists will do that, such as imagining different modalities of evolution or different ways that genetics could operate. If the genetic code were different, for example, that would be an interesting thought experiment that people have done. So yes, thought experiments are still a part of science and probably should be and always will be.
Thank you. The next question is from Frederick, who asks, what is your why it seems we are alone in the universe? Do you think that it will always be the case, or is there something to the rare Earth hypothesis?
You have to rewind that. It cut out a few key words.
My apologies. What is your opinion on why it seems we are alone in the universe? Do you think it will always be the case, or is there something to the rare Earth hypothesis?
The fact that we appear to be lonely or alone in the universe is possibly just an artifact of the very short period of time we've been looking or listening. Remember that humans have only had technology for 50 or 60 years, computers and space travel, for instance, and so we're just in a very early phase of exploring the universe and finding out our place in the universe and seeing if there are others like us. So it's maybe a matter of time before we encounter companionship or others out there. So that's one way to look at it, that we've been doing it a very short period of time. The rare earth hypothesis sort of builds the apparent isolation of humans as living creatures in the universe, builds it into a premise that the earth is actually rare, and it uses specific attributes of the earth, sun, moon system to argue that our situation is very unusual, that most Earth-like planets would not have our particular set of properties that allowed complex life to evolve. I would say the various arguments that are part of the rare earth hypothesis have been largely deconstructed, not completely, but largely deconstructed, including the idea that you need a large moon to stabilize the tilt axis and the orbit of the Earth, involving the particular mass of the Earth, involving the attribute of plate tectonics. Many of these things are considered to be somewhat favorable to life. They made life easier, but not necessarily. Some of them have not made life easier, and it also depends on what kind of life you're talking about. So I think rare earth has had its time, and it's now not favored by most planetary scientists as a hypothesis for why we might be special or isolated.
Terrian would like to know, do you believe that wormholes exist and that we could potentially tear the fabric of space-time?
Wormholes are a theoretical concept. They can be found in the idea of general relativity, that space-time can have ruptures and space-time can have interconnected parts, which is sort of what a wormhole is. It's a sort of portal, if you like, between two disparate locations in space and time, sort of a cleft in space-time. So it's theoretically possible, but there's literally no evidence they exist in our universe. And there may be reasons to think they don't exist, because space-time, as far as we measure it on very large scales, is very fundamentally simple and flat and Euclidean. The rare examples of black holes, because they are rare objects, is the only real exception to that. So I would say that makes the possibility of wormholes there. It exists. They do have the possibility to exist. That doesn't mean everything that could exist in a theory, like general relativity, does exist in our universe.
Outlearn would like to know, before the Big Bang, what existed and for how how long?
So we don't know. The Big Bang is a model or a theory that only describes the evolution from a dense, an extraordinarily dense and small and hot state. That's all it does. It does not talk about the origin itself, the very instant of creation, the Big Bang itself. It doesn't talk about what caused it, and it doesn't talk about what came before. All of those questions can be asked. You can always ask a question of nature or science, but they don't have an answer within the Big Bang theory. And so they lead to speculations about quantum genesis and other quantum states and string theory and the multiverse. There's a whole set of topics that are interrelated. But it's important to bear in mind that these are entirely speculation, not even a little bit observationally tested. So the simplest answer to say is we can't answer those questions right now.
The next question is from Ellensburg, Washington. Will we be able to see the black hole at the center of our galaxy, or any other galaxies for that matter, with JWST?
No, JWST is not really a good black hole observing machine. There's a couple of reasons for that. First of all, the black hole events, the black hole observations we've seen, the spectacular images from the Event Horizon Telescope, are made at radio wavelengths. Far longer than the wavelengths James Webb uses, a factor of 1,000 or more longer. And those waves travel freely through the dense dust and gas at the center of our galaxy. So only radio waves could have shown us the black hole in the center of our galaxy, viewed through the disk of the galaxy, or the black hole in M87. That was the other measurement they made in 2019. James Webb, while it is working in the infrared, and the infrared waves penetrate dust and gas better than optical light, the center of our galaxy is still opaque to James Webb. So James Webb will penetrate star-forming regions nearby and tell us about star-forming regions, but it won't be able to penetrate the murk that surrounds black holes at the centers of galaxies.
So there has been a recent announcement that there will be, or potentially, a solar flare, a solar storm that hits Earth tomorrow. And Anelli Craig would like to know, are there any actions that one should take to protect one's data or privacy with either tomorrow's possible geomagnetic storm or with any other geomagnetic storms? How do we handle these on Earth?
Well, the way they're really handled, the resilience of the grid is an issue, and people are aware how vulnerable it is. So people, big power companies and, national level entities are working on the resilience of the grid. And so there's enough redundancy that hopefully the grid won't completely go down. As far as data goes, most data, of course, resides in the cloud, and the same principle applies. These massive servers that hold most of the world's data are in buildings that have a fair amount of electromagnetic shielding. That's sort of built into the building construction. That's not going to insulate them from the most massive possible, flare and electromagnetic pulse that results from it. But the redundancy of data in the cloud means that it's often held in more than one location, and the odds of both locations or more than two locations going down are pretty small. At the personal level, you just use the same principle of redundancy. So just make sure when you back up all the data that matters to you, you have multiple ways of doing it. And I suppose the even safer way is to make one of those a detachable hard drive, terabyte hard drive or whatever, that you put in a safe or something like that, a shielded container.
Our next question is from Richard Tennis, who asks, part of a Chinese satellite just fell onto land in Borneo, and recently parts of a SpaceX rocket fell in Australia. Is there any way to prevent so many things from falling out of the sky?
Yes, there is. These things don't have to fall out of the sky. The Chinese rockets are a 23-story rocket, a huge amount of hardware. It was known that this was going to fall to the Earth, and all the Chinese did was guarantee, based on its orbit, that the odds were it was going to fall either in the ocean or in an extremely isolated area. And we know enough about how orbital trajectories happen as something falls into the atmosphere and experiences drag. That's a fairly reliable thing to do. But it's a matter of choice, and it's carelessness in the end that causes rocket debris to fall to the Earth, because it doesn't have to. SpaceX, of course, is designed around reusable rockets, so SpaceX, as a general business principle, doesn't like to jettison or discard things, because it's destroying hardware that's expensive, and it's a waste, as well as potentially being dangerous. The Chinese are poorly socialized in this regard. They've blown up one of their own satellites, which is a very nasty thing to do, creating thousands of pieces of debris that everyone has to deal with. And so there's nothing really we can do about a Chinese government if they want to behave that way. But in general, spacecraft do not have to fall back to Earth, and we do not have to rain debris on the planet. It may cost a little bit more to stop it happening, but it can be done.
The next question is from Faisal, who asks, can you explain how a gravitational lens can reveal dark matter?
Sure. Gravitational lensing is a prediction of general relativity, which says that mass energy curves space-time. And so if you have a single massive galaxy, say, which is embedded in a dark matter halo, we know, which has 80% of its total mass, or a cluster of galaxies where dozens or hundreds of galaxies are orbiting within a dark matter halo that also contains about 80% of the total mass, then light passing through that region will be bent by the total mass, because the gravitational lensing doesn't care whether the mass is visible or not. It just says that mass energy bends space-time, and it doesn't matter if the mass is dark matter or normal material like the atoms we're made of. And so gravitational lensing is a reliable way to measure dark matter in these ways, by looking at the bending of the light, by making a gravitational lens model using simple equations actually of general relativity, and you can map out dark matter this way.
The next question is from Chris Plord, who asks, will there ever be a Saturn mission that takes images of the rings that are close and detailed enough to show the individual particles or chunks that make up the rings?
There is one mission, an outer solar system mission, that's on the drawing board but hasn't been selected, hasn't even gone through a first selection phase, that is trying to follow up the Cassini mission. Remember, Cassini was the mission that gave us the best view of the rings and many of the moons of Saturn, and it did a wonderful job in its more than decade-long mission before it plunged into Saturn as in its death spiral. So there's a successor mission that's envisaged for maybe 15 or 20 years from now. That's when it would get to the Saturnian system. And it would do the very risky thing, of course, of going through the ring system. So to get close-up pictures of the rings, you have to get near the rings. And the particles are not completely confined to the rings. They distribute near the rings too. So you're increasing the probability that spacecraft will take hit, be damaged, or even destroyed. But yes, there is a mission planned for, say, 20 years from now that'll give us a superb view of the rings and do more exploration following on from what Cassini did.
The next question is from Aaron, who asks, are we comparing the Earth's atmospheric composition with the atmospheric graphs of other planets while searching for life on extraterrestrial planets?
Yes, we're definitely using Earth as a template for what a living planet looks like, because it's the only living planet we know. So our particular combination of 4/5 nitrogen and 1/5 oxygen, plus small amounts of trace other elements. Argon is the third most strong ingredient. Argon is an inert gas, so it's not a biomarker. Yes, our atmosphere is definitely a template, but the trick is, or the problem or the issue is, that an atmosphere of a planet is not unchanging. The Earth spent 1.5 billion years with a very low level of oxygen, only 1% or even less than 1%, before oxygen was pumped up in the atmosphere about 1.5 billion years ago. So the atmosphere you think indicates life now may not be the atmosphere that indicated life in the past, say when methane was the mode of metabolism of microbes and oxygen wasn't. So it's tricky. There's no one size fits all. There's no one template for looking for biomarkers. You need a suite of models, and in the end you'd have to have a whole set of different metabolic models of life to see what atmospheres they generate.
The next question is from Axolotl Love. Why aren't hot Jupiters stripped of their gaseous atmospheres if they orbit so close to their stars?
Well, some of them are, and some of them have been, and some of them will be. So yes, hot Jupiters, when they migrate inwards and then park on a tidally locked orbit where one side is facing the star, and they're incredibly close. The typical hot Jupiter, well, the prototypical hot Jupiter was 51 Peg B, the first exoplanet discovered in 1995. It's half the mass of Jupiter, and it orbits its star, its sun-like star, in 4.3 days. So incredibly tight orbit and incredibly high temperature. And that temperature, yes, is enough to slowly ablate or boil off or strip off the atmosphere of a giant planet. And so there may be some systems that we might find where we've seen a hot Jupiter after its atmosphere has all been boiled off and maybe just the rocky core remains. Those would be hard to detect, however. And of course, when the atmosphere is boiled off, the reverse of the migration may happen where the rocky core spirals out of the system and is lost.
The next question is from Nita Frank, who asks, if Mercury has a 75% iron core, why doesn't it have a magnetic field like Earth?
That's a good question. It's really to do with mass or size. So the ability to retain a magnetic field is also a function of mass, because the magnetic field lines, the concentration of the magnetic field lines depends on the size and the mass of the metallic and the rocky core. And Mercury's core, while it has the right ingredients chemically, it is physically a very small planet. And that means that even if a magnetic field had been formed in Mercury early on, the magnetic field will very slowly dissipate over time, and so it's hard to imagine that it could retain one. Mars also has no magnetic field, and it's also a small terrestrial planet.
Arya asks, how can one planet have both extremes of hot and cold? Is it related to the magnetic field in any way?
Well, hot Jupiters and planets that are tidally locked to their stars are examples of this. Depending on the atmosphere and the mass of the planet, any planet that's tidally locked to a star has the one face pointing to the star and the other face pointing to the depths of cold space. And if that atmosphere is very thin, then the sun-facing side will be baked or boiling or melting even to the level of melting rock in some cases, and the other side will be frigid, temperatures far below the freezing point of water. So tidal locking can create these extreme dichotomies. And Mercury is a good example. Mercury is tidally locked to the sun, and we know that Mercury has a very hot side facing the sun, a very cold side away, and then this little slender region called the terminator where temperature is intermediate and where people have imagined in some fantasies of space travel that we could eventually have a living situation in that little tiny little habitable strip.
The next question is from Mysterious Gamer. What subfields are there in astrophysics that I can study, like planetary science? So I'm not sure if they mean astrophysics specifically or astronomy. Can you talk about some of the related fields or subfields for astronomy and astrophysics?
Sure. I mean, astronomy at the level of an undergraduate education or graduate education does have subfields, and they sometimes parse into the types of courses that you take. Obviously, one big division in the field that people essentially view as a fork in the road when they want to make a career is between general astronomy or astrophysics and planetary science. So planetary science is a huge field in its own, and it involves more geology, it involves atmospheric science too. So the interdisciplinary nature of planetary science is different from astronomy. Cosmology is obviously a huge field of astronomy that has its own expertise, its own theory, general relativity, and the expanding universe. Plasma physics is another example, dealing with the hot plasmas of the universe. Stars are hot plasmas, but there's also diffuse plasmas in interstellar and even intergalactic space. So these are all big subfields. And then high energy astrophysics. There are very high energy particles that are produced in astrophysical environments when accelerating from magnetic fields, being driven by gravitational potential energy in a collapsed object like a black hole or a neutron star. And so these high energy phenomena essentially form a subfield because the mathematical and physics methods required to understand high energy radiation and high energy particles are a little different.
The next question is from David McKenzie, who sent an email. What science is the Nancy Grace Roman Space Telescope designed to do, and what is the difference between it and what the JWST will be doing?
It's really very different because JWST, James Webb Space Telescope, is an infrared telescope with very small field of view. I probably remember that when the first science data images were released and everyone looked at that deep field with thousands of galaxies and gravitational lensing, it was pointed out that this field is about the size of a grain of sand held at arm's length. That's a tiny piece of the sky. And so the field of view, in terms of what this telescope can see at any one time, is really small. It's designed for going deep in a very small area of sky. The Nancy Grace Roman Space Telescope is quite different. It uses a more modest mirror. It's at the moment considered to be a 2.4 meter mirror, but that may change. But it has very wide field capabilities, so it's much more of a survey telescope in space. And it will be very powerful because it's an exquisite mirror, the one that they're thinking of launching, and the CCDs behind it will be enormous. It's much more of a counterpart to the Vera C. Rubin Observatory, formerly the Large Synoptic Survey Telescope, which has also got wide field CCDs and will be doing survey science. So Nancy Grace Roman Telescope is really complementary to James Webb Space Telescope, and having both of them in operation in space will be amazing, actually.
So I think this next question could be answered in a few ways, but P51 asks, what part or parts of the universe are the least observed of you?
The end of the question got chopped.
Okay, what part or parts of the universe are the least observed from Earth's view?
The parts of the universe that can be seen very well are most obviously the far side of our galaxy, because we're in the disk of the Milky Way galaxy about 2/3 the way out, just beyond the Orion spiral arm, and the galaxy is full of gas and dust, and when we look through the disk of the galaxy, we can't see the galactic center with visible light. It's like looking through a closed door. So we can't see the whole other half of our galaxy on the other side of the galactic center. So that's one of the least observed. And that means that dust extends far enough above and below the plane of the galaxy that when you're doing galaxy surveys, so looking at more distant galaxies in directions near the plane of our galaxy, you can't do very well because dust obscures them. And so it's more than just the disk itself, it's a strip around the disk, and it's called the zone of avoidance actually by extragalactic astronomers because you just don't get complete data. So that's the biggest censoring, if you like, of our view of the universe, just from our particular vantage point in the galaxy.
Excellent. All right, well, it is 11 o'clock. We are going to wrap it up with one final question from a live participant. Thank you all for joining us. We have another one of these next week, and then a break. If you have not liked and subscribed to our channel, make sure you do that so that you can get those announcements for future live sessions. Next week will be on Twitch, so we'll see you all there. The final question is from Nita, who asks, if everything in the universe is expanding or going away from each other, how is it that galaxies ever collide?
Yeah, it's a good question. If everything was expanding just smoothly and seamlessly, they would never collide. However, gravity has a long reach. It's an infinite range force. And so when galaxies happen to be close to each other, they can be bound to each other by their mutual gravity, which exempts them, if you like, from the cosmic expansion. The Milky Way and Andromeda is an example. Milky Way and Andromeda are falling towards each other at 100 kilometers per second and will collide in about 3 or 4 billion years. So you can have certainly parts of the universe where the galaxies are captive because of their mutual gravity. It could be a pair of galaxies, a group, or a huge cluster of galaxies like the Coma cluster with thousands of galaxies, while the universe on an even larger scale is expanding all around them. So that's really what's happening. on the largest possible scales, hundreds of millions of light years, the cosmic expansion is smooth and uniform. But on smaller scales of galaxy-galaxy distances, the galaxies can be captive. So that's a good question to end with. And I think I'm just going to, Matthew and I have to talk about this, but I'm not going to be here next week, as it turns out. So we will have to reschedule, or if our next live session had been thought for next week, it's going to be later than that. But thanks to
Excellent.
Matthew.
Well, I apologize. So we'll make sure to get an email out about that. Yeah. And then I at the beginning, but there was a mistake in the email that I sent out also about the August 22nd live session. It is on August 22nd. It's just that day is a Monday, not a Tuesday. So I will send out another email soon clarifying the next live sessions.
Okay, thanks to everyone for their good questions, and to Vicki and Matthew for running the session.
Excellent. All right. We appreciate all of you. We are excited to have you join us again next time. Take care, everyone.